Now we will see out of order execution. So this is also very important for understanding meltdown, right. So that is the second step, as I told you in the 3 steps. I have covered out of order in deep detail in my information security 2 course, but I want, if you want, you can go and look into it, but I will give you a very quick 10-minute summary of what is out of order. There are 5 stages in execution of an instruction. The first one is the fetch the instruction and increment the program counter. The second is decode the instruction. The third is fetch the data. The fourth is execute the instruction. Fifth is store data. In an ideal scenario, let us assume that each takes 1 unit of time, whatever that unit be, nanosecond, picosecond, 1 unit of time. Each instruction will take 5 units of time. So if I have 10,000 instructions, then it will take 50,000 units of. Now the interesting thing, as I told in the earlier course, when an instruction is fetched, all the remaining 4 units, namely decode, fetch instruction, fetch data, execute instruction and store data, they are not doing anything. When the instruction is decoded, all the remaining 4 stages like fetch the instruction or fetch data or execute instruction, store data, they are not doing anything. So that 5 stages of the instruction is executed by 5 different hardware pieces. The hardware in charge of fetching the instruction will do nothing after that. The hardware in charge of decoding the instruction will only decode the instruction. In the remaining part it will not do anything. So every unit ideally is executing for 1 unit of time, and an instruction takes 5 units, in which each unit will take 20% or 1 unit of time, ideal scenario, just to understand. The remaining 80% of the time that each unit is free, ideally it is free. So can I reuse it, can I use it? This is the basic observation that motivated the notion of pipeline. In pipeline what happens, first I1 comes, I am sorry, you should have a very close look at your screen, I do not know why I made that color. So I1 comes in, then when I1 is decoded, I2 is fetched. When I1's data is fetched, I2 is decoded and I3 is fetched. When I1 is executed, I2's data is fetched, I3 is decoded and I4 is fetched. When I1's data is getting stored, I2 is executed, I3 is fetched, I4 is decoded and I5 is fetched. So I3's data is fetched, I4 is decoded and I5 as an instruction is fetched. So the first instruction finished at 5th unit, second instruction at the end of 6th unit, just 1 unit delay it can. So your 10,000th instruction at the end of 10,004 units it will finish. So now your entire thing becomes 5 times faster at this point of time. Now the ideal scenario is, I always assume that executing an instruction which is happening at this 4th stage as you see on the slide will take constant time, right. So will take the same unit of time, whether I am doing addition or multiplication or division or floating point addition or floating point multiplication or floating point division or whatever bitwise, and everything I assume it will take unit amount of time, which is not the case. So this is the ideal proof or ideal scenario for me to explain pipelining in say 2 minutes, which hopefully I have done and hopefully you have understood, but this is not the reality. So the execute instruction, there could be different instructions taking different amount of time, and that leads to the concept of what we call as the out of order execution processes. So what has happened here is that what we have done is that there is one fetch, that instruction gets decoded, one data gets fetched, then there are multiple execution units. Each unit is capable of doing some operation. Each unit, all units need not be symmetric. So there can be some units which is doing load and store, there can be some units which are doing add, integer arithmetic, there will be some unit which is doing single precision floating point, there will be some unit which is doing double precision floating point, like that. Now when the instruction is decoded and it is available, now the hardware by looking at the instruction has to decide whether it should go, it is an integer instruction or it is a boolean instruction or it is a jump branch transfer instruction or it is a floating point instruction, it is a single precision floating point or double precision floating point. Then there are several instructions like SIMD, single instruction multiple data instruction. So it has to find out what and correspondingly allocate to that unit. as I have multiple units. So, I have n execution units, not necessarily everything be symmetric, but for a simple understanding of the out of order execution, let us assume that all these units are all symmetric, every unit is capable of doing every operation. Okay. Now, suppose I have say 4 FMLs floating point multiplication, while 1 floating point division. Floating point division, let us say floating point division is the first instruction to be executed in your program order, in your assembly program order. FDiv comes first, followed by 4 FMLs. FDiv will take 40 cycles, FML will take only 10 cycles. Let us say all these units can do floating point. I do the FDiv in 1 unit. By the time FDiv finishes, the remaining 4 FML can also finish, right. So, that is a very interesting thing, right. So, FDiv comes first, but FML 1, FML 2, FML 3 comes after FDiv. Now, before FDiv actually finishes, FML 1, FML 2, FML 3 can finish and be ready with the answer. The moment FDiv finishes, all the answers can be sent back. Now, when is this possible? If the result of the division is not used by the subsequent instruction, then what could happen, that 4 instructions can execute together at the same place, and this is the out of order execution, introduction to out of order execution. So, what has essentially happened here is that the 4 multiplications, at least 2 or 3 of the multiplications that followed FDiv got executed, finished, and they were ready before FDiv finished. So, that means that there is a program order, there is an assembly program order in which the instructions appear, and in this case an instruction that came after a particular instruction actually finished its execution before the previous instruction. Like FML has come after FDiv, but before FDiv has finished, a couple of FMLs can also finish, and this is possible if the input to the multiplying instruction, the data to the multiplying instruction should not be the output of FDiv. If FDiv is calculating the output of the instruction, then FML has to wait, but if it is not doing, then FML can still proceed and it can keep the answers ready. As soon as FDiv finishes, this can basically put the answers back into the memory. So, this is how the advanced pipelining work, and we have explained this in a good detail in the IS2 course. Now, I am just basically covering this Tomasulo algorithm because this is something very important for us to understand the meltdown. This I have done in IS2 course, but I will again do this. So, this is how the entire microarchitecture basically looks like. So, there is an instruction fetch unit which can fetch 1 or 2 or many instructions, and then there is a register status indicator which says that if the register status indicator is 0, that means the latest value of the register is in the register file. If the register status indicator is 1, that means the latest is non-zero, say some I, that means the execution unit I. Suppose the register status indicator is 2, that means the execution unit 2 is currently computing the value of the register, and that is the latest value. So, the latest value, if I have a non-zero value in the register status indicator, that means the latest value is not in the memory, it is currently under computation by one of the execution units. And what we also do is, instead of just storing something, we can store that, say the value 3, means the current value of the register is not in the register, but it is going to be output by the execution unit 3. So, this is how the whole thing, this is how the register status indicator is. After the register status indicator, there is one unit which basically schedules the instruction depending upon each unit. Let us assume that each unit cannot do everything, every unit cannot do everything, there will be some unit doing integer arithmetic, some unit doing floating point arithmetic, etc. There are multiple floating point units, multiple integer units. Now, the register status indicator, subsequent to the register status indicator, the instruction should be, if I have an integer instruction, it should go to an integer execution unit. If I have a floating point instruction, it go to the floating point execution unit. So, some scheduling happens there, and this scheduling happens dynamically, that is why it is called a dynamic scheduling. Dynamically means when the program is in execution, it is not done by the compiler, it is done by the program when it is in execution. So, what will this, so if I get a load store instruction, or say let us say I get an arithmetic instruction, and let us assume without loss of generality on the slide when you see the execution unit 1 basically can do arithmetic instructions. So, and that is free. Now your instruction is basically put into this execution unit 1. It comes to the reservation station and then starts executing at execution unit 1. After that, the result of that is basically written on the common data bus, which goes to the register file or memory, right, wherever the destination is, and also that values are fed back into this execution unit. Immediately they are fed back before it actually goes to the memory unit or register file, etc. The answer is basically fed back to all these. So these two things happen in parallel. I send something to the register file or the memory saying, oh, this operation is over. Before this actually reaches the register file or the memory, there can also the whole data actually gets populated back in some of these reservation station if there is a need, right. So that is very important, because if I want to implement out of order execution and of a very strong out of order execution, when I want to implement that, I need to have these type of execution profiles, right. So I need to start executing multiple instructions at the same time, and if that is not possible, then you will not get the performance. And that, so this is extremely performance driven. The out of order execution is performance driven, and this entire dynamic scheduling that we are talking of is also performance driven. So instructions, so let me just very quickly sum up this slide. The instructions are fetched one by one and they are decoded to find the type of operation, whether it is add or subtract or anything, and and also it is decoded to find the source operands for that operation. So if I say add two numbers, where are those two numbers stored? Is it in memory? It is in general purpose register. That is the sort of input that is needed from the instruction fetch unit. So as you see in the slide, the register status indicator indicates whether the latest value of the register is in the register file or it is currently being computed by some execution unit, and if the latter is it states the execution unit number. So the register status indicator will say 0. 0 means the current value is there in the register file. If it says 5 means the current value is currently computed by execution unit 5, right. So you wait for that and take the data, right. So that is what I am reading the last sentence. Register status indicator indicates whether the latest value of the register is in the register file or currently being computed by some execution unit, and if the latter is true, it states the execution unit number. So the register file itself will say if it has 5, it will say the latest value is going to be written by 5. So what happens after this? You come after the register status indicator, you just come, if all the data input data are available, then you start executing the program. If some data is not available, then what you do, you keep waiting on the bus, right. And whenever suppose I say I need the value of some register, and it says that the execution unit 5 is actually reading that register, currently handling that register. So I go to the reservation station marked in red here and wait for 5 to give an answer. When 5 completes, it writes back in the common data bus, that whatever brown color that you have on the common data bus, it writes the value which will actually go to the register file or memory file, but at the same time it also gets propagated back into this through the violet bus onto each one of those reservation stations, right. Once so when I am waiting for say unit 5, 5 writes there, so whenever I see a 5 writing into that bus, so when something is written on the common data bus, they also write the execution unit number. So when I am looking at the violet line, I find execution unit 5 is coming, so immediately I can start taking that data and start handling it. So these are all some of the very interesting important fact about dynamic instruction scheduling. So every execution unit, as you see on here, writes the result along with the unit number onto the common data bus, which is forwarded to all reservation stations, register file and memory. Okay, so you got a quick overview of what we are calling as the out of order execution. Now we are coming to this program. Suppose I have say this is a block of instruction I plus 1, I plus 2, I plus 3, right. Now what I do at I is I go and my objective is to go and read one OS page and show that I have read it. So what will happen, instruction I will try to move the OS location to a register EBX, right, when instruction I gets executed. What will happen is the instructions I plus 1, I plus 2, I plus 3 are also being executed, because it is a superscalar processor, and suppose there is no data dependency between the move instruction and the 3 transient instructions, then basically what will happen is the instruction I gets executed by the time your instruction I plus 1, I plus 2, I plus 3 are also being executed. What will happen is I will encounter an exception, because I am trying to read an OS page, move OS lock comma IBX. So first see the ith instruction, it will immediately get exception. So all the changes caused by I plus 1, I plus 2, I plus 3 etc. have to be rolled back, because now an exception has come. Now after curing this exception, again I start running I1, I2, I3, that is the correct way of doing it. So but then it's quite a large amount of time. So when I encounters an exception P1 to OS access, then all these changes that are done by I plus 1, I plus 2 and I plus 3 are basically annulled, okay, or we call it as rolled back. Please note here that there is a small window of time, very small window of time, from the time I writes to the register EBX and the instance at which the exception is triggered, right. So the register modified by I can be accessed by I plus 1, I plus 2, I plus 3 in this small window of time. So essentially what happens is, for performance reasons I as a process try to read a OS page, right, some entry in the OS address space. Now when will that detect? So two things happen. One thing is there is something sent to verify whether I can access or not, right, whether it is a user mode page or supervisor, can I access or not. Another side, it will go and fetch and keep, it will not go and commit it into a register, right, so that when this check gets over I can just take that and commit it and take it forward, okay. So what happens essentially is, when when I go and access a kernel space, a memory location in the kernel space, the data is actually fetched and it is ready before actually an exception can happen. So the data, that instruction gets executed per se, but then when an exception happens everything is rolled back, right. So this is very 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 important here, right. So this is because I have things like out of order execution, which allows the next instruction to execute when I am still executing, or the next instruction to go forward while I am still executing, right. So that is one thing. So that is the major part of what we say is the out of order execution, and it sometimes is also called speculative execution. There is a branch, so after that conditional branch there are some instructions, we do not know whether that instruction, whether that branch will be taken or not taken. So we just speculate that okay, the branch will be taken, and then go start executing those instructions. If your thing is correct, it's fine. If your thing is wrong, then you roll back. Roll back is a very costly affair. So that is also one very important thing that we need to keep in mind. So what happens here? I basically access a kernel location and that value is already brought and stored in EBX. After that only somebody raises an exception. Now along with this move there could be other instructions like transient instructions which are waiting for EBX, right. So what will happen is when this instruction move OS log comma EBX executes before an exception is raised, as you go back to see here, let us say execution 2 unit is executing, that value of the other 3 transient instructions are waiting in execution 1, 3 and 4 for the value of EBX. When execution 2 unit finishes and when it is trying to write into the register or memory or so every other execution 1, 3 and 4 will get this value through that that violet bus, it will get back that value. So I will have transient instructions, say suppose I am reading into a kernel memory into in a register EBX, all the 3 transient instructions would now have the value of EBX. After this only there is an exception saying, hey Vati, this is wrong, he should not have accessed. Then the hardware itself goes and rewinds everything, it undoes everything, right. So by the time this hardware undoes something, the entire meltdown attack is some instructions get executed, right, before the exception is raised and done, and that thing basically we need to that is the point where these instructions get executed, and by executing these instructions they somehow see that some information is leaked, right. So let me again tell you, I am having an instruction say executing in execution unit 1 which is going to basically read a kernel address space into a register EBX. Then there are 3 transient instructions as you see which all will start using EBX. So all those 3 transient instructions are waiting in execution 2, 3 and 4 waiting for this value of EBX. Now the first instruction will read from the memory OS kernel location space and it will come here and it is about to go and write into memory. On its way the data while it is going to memory, it will also get fed into execution 2, 3 and 4. They are waiting for this execution 1 unit's result. The moment it comes, your execution 2, 3 and 4 will have the value of the kernel address space and it will do something so that it can communicate to the external world, this is the value, correct. So this is the basic thing where out of order execution has helped us. If it is in order, then there is no bypass that I need to do, there will be no multiple units, there will be no violet bus, and so it is gone. But now since I have done out of order, I am now in a position to access the EBX. Just this is the code sequence. So instruction I gets executed, instruction I plus 1, I plus 2, I plus 3 are also being executed. Now I encounters an exception, P1 to Ix has access, changes are rolled back, and the changes caused by I plus 1, I plus 2, I plus 3 are also rolled back, right. So this is the important thing. So that is why we still now we are thinking that we are safe. Now the I tries to access the kernel address space, then immediately and store it in EBX. Now that happens, and before that the hardware says that this should not happen. Actually the other 3 instructions which are waiting for this value, say EBX, will get that value of EBX, and now they can start doing whatever they want. And at some point of time they will all be removed because I itself is wrong. So I plus 1, I plus 2, I plus 3 will get annulled. All the things that it has done will get annulled because of this. But by the time it gets annulled, that is what we were said, there is a small window, and in that window we can basically leak the information of EBX to the entire external world, right. So this is basically the important thing. So now at a micro architecture level I have registers and the registers store value. The registered modified by I can be accessed by I plus 1, I plus 2, I plus 3 in this small window of time before everything gets undone. It will not, so the the values of this EBX, the instructions which are I plus 1, I plus 2, I plus 3, it will not only take this latest value of EBX, but then it can take any value from there. So, the kernel data can now be read by I plus 1, I plus 2, etc. And however, once the exception is raised, all the instructions are rolled back and all these will go. Somehow before I lose this information as an attacker, I need to basically somehow store that information in some form, so that the parent process basically access it and then leaks it out. So, this is the so in the next section we will talk about recovering from exception, and then we will continue with the meltdown attack accordingly. Thank you.